Where did we leave off last time? So a few things I want you to remember. I want you to remember about flows. Right, so we're talking about directed graphs. There's a source, there's a sink. Every edge has a capacity. The goal is to push as much stuff as possible from the source S to the sink T, subject to capacity constraints. You can't overload anyone's capacity, and subject to conservation constraints. The flow into a vertex should be equal to the flow out, except for the source and the sink vertex. So those are flows. A really important concept is that of a residual graph. So for the next few lectures, often when we're talking about a graph, it'll be the residual graph. So it's really important you remember what the residual graph is. So how does that work? So if you have a graph G, and you have a flow F in the graph G, then there's a corresponding residual graph G sub F. Each edge of G spawns two edges in G sub F, one going forward, one going reverse. The forward arc is given in the residual network capacity UE minus FE. So this is just the room left on the edge to push flow forward. Okay, so that's the forward edge in the residual graph. The reverse edge corresponds to an undo operation. So if you've already pushed F sub E units forward across it, then you have capacity F sub E to undo it to push it backward. Okay? So that's the residual graph, and we talked about the Ford-Fulkerson algorithm. What's the algorithm? Just whatever the current residual graph is, you try to find an ST path where all the edges have positive capacity. If you find one, pick an arbitrary such one, push as much flow as you can on that path, subject to the capacity constraints, and then terminate when you don't have any ST path in the current graph G. Okay? That was the Ford-Fulkerson algorithm. And so we argued last time that it terminated. We haven't yet argued correctness. That is, the flow that it terminates with, how do we know that it's a maximum flow? And again, there's sort of the broader question here, which we're wondering about in particular for maximum flow, but it's going to be a recurring theme through the first half of 261, which is how do we know when we're done? Okay? So we have some algorithm, we think it's a good algorithm, and at some point it stops. How do we know it didn't stop too early? How do we know it stopped with the optimal solution? In this case, a maximum flow, okay? And again, this question is sort of interesting even just without an algorithm. So even if someone just handed you on a silver platter, say, an alleged maximum flow, how could you convince yourself that it really is a maximum flow, that there isn't some other flow out there in the world which sends even more stuff? So I left you with this network as an example. So the green numbers are the capacities, the red numbers are the flows. Okay, so this is a flow of value 3, right? It's sending 3 units of flow out of S. And if I tried to claim this was a max flow, would you believe me? And if so, why? Okay. There's all these edges with capacity 100, and somehow could it really be true that the maximum flow you can push from S to T is only 3? Okay. All right. So that brings us up to speed. Any questions about the review? Okay. All right. So I gave you a claim last time answering this question, how do we know when we're done? The claim was that if the residual graph has no ST path, then the flow F has to be maximum. We didn't prove that, but if that claim is true, then the Ford-Fulkerson algorithm is indeed correct. It does indeed solve the maximum flow problem. Why? The stopping condition of Ford-Fulkerson is exactly that there's no augmenting path in the residual graph. Okay? So if that's a sufficient condition for optimality, then we're all good. So it's going to be convenient to actually prove a stronger statement, which is going to be the first thing I do this lecture. And from the stronger statement, we'll also be able to derive the famous MaxFlow MinCut theorem. So to state this stronger result, I need a definition. Probably, you may have seen this before, for example, when you studied minimum spanning trees, that of a cut in a graph. So you have a graph, source S, sink T, an ST cut, or sometimes I'll just call it a cut. That's a partition of the vertices into 2 sets A and B. The source is in one of the sets, the sink is in the other set. Okay? So it's a partition AB of V. So each vertex is in exactly one of A or B. And it should be the case that the source is in A and the sink is in B. Okay? And kind of the generic picture you want to have in your mind, for what a cuts look like. So here's a graph, here's a source, here's a sink. Here's a cut. This is your A, and this is your B. Okay? So whenever you have a cut in a directed graph, it naturally buckets the edges into 4 different types. You got your edges that are just hanging out inside A. You got your edges that are just loitering in B. You got edges going across the cut from the source side to the sink side. And you've got edges going backward from the sink side to the source side. Okay? So that's a ST cut of a graph. Okay? And as we'll see, it's sort of a dual, in a sense we'll make precise later, to maximum flows. Okay? All right. So that's a cut. Let me tell you what the capacity of a cut is. So the capacity of a cut, what you do is you look at all the edges that stick out of the cut, okay, that stick out of A, and you add up all of their capacities. Importantly, you do not look at the edges that stick into A. Okay, you ignore them for the capacity computation. Okay? So the capacity of a cut AB is, by definition, the sum over the edges sticking out of A of their capacities. And I'm going to be using the notation delta plus of A is the edges sticking out of A. Okay, so these are the edges in delta plus sticking out. And then delta minus is the ones sticking in. Okay, so these are delta minus here. All right. So that's a cut, and that's the capacity of a cut. For example, suppose we take A to be the vertices S, let's call this W, let's call that V. Suppose we take A to be S and V, and we take B to be V and T. Sorry, A is S and W. So what's the capacity of that cut? Okay, so what's up with a cut? So we don't look at edges that are inside A, so we ignore this 100. We don't look at edges that are inside B, so we ignore that 100. We don't pay attention to edges that stick in, so we ignore that 100. So we're looking only at the ones that stick out of A. We have that one, and that one. Okay. So the capacity of that cut would be 3. So example. Capacity of SW VT equals 3. Okay? It's not an accident that that's the same value of that flow. More on that in a second. Okay? All right. So I should say other cuts in this graph have much larger capacity. Right? So another cut would be you just take S, the source, to be one side. You take the other 3 vertices to be the other side. So the capacity of that cut would be 101, right? So much, much bigger. Okay, so different cuts can have very different capacities. What turns out to be of interest to us is the minimum cut, the cut that has the minimum capacity, okay? So here's the theorem which generalizes the claim from last lecture and proves correctness of Fold-Ferguson. And it's not too hard to prove. We're going to prove it. It'll take us a little bit, but it's not too bad. So for a flow F in a graph G, the following are equivalent. Okay, so TFAE, that's the following are equivalent. So I'm going to write down 3 statements. This means either all of them are true or none of them are true. Those are the only 2 possibilities. Okay, so condition 1, something we care about. F is a max flow. Property 2, there exists an ST cut AB such that the value of F equals the capacity of the cut. And the third statement is that the residual graph has no ST path. Okay. So the claim from last lecture was the assertion that 3 implies 1. Okay? That's what we claimed at the end of the last lecture. This is saying any one of these 3 statements implies the other 2. Okay, so it's giving us only more information. Question? Okay. So any questions about the statement? Otherwise, we're going to go on to the proof. Yeah. The following are equivalent. Either all are true or none are true. So any one of them implies the other 2. Other questions? Yep.
Could you clarify what you mean by has no ST path?
Sure. So GF is a directed graph. S and T are vertices. There's either a path from S to T or there isn't. This is saying there isn't one. Other questions? Statement clear? Okay. All right, so the way you prove the following are equivalent statements is you just do a cycle of implications. Okay? That means if any one of them is true, it sort of just percolates through and all of them are true. Okay, so we're going to show that 2 implies 1, 1 implies 3, and then 3 implies 2. Okay? All right, so proof. So the first step, 2 implies 1. Okay? So the claim here is that for this implication, it's enough to show that for all flows F and for all cuts AB, ST cuts AB, the value of F is at most the capacity of the cut. That is, any ST cut of a graph bounds above the value of any flow in the graph. Okay? So that's the assertion. So I need to just show 2 things. First, I have to argue this is true. But secondly, just take it on faith for a second that this is true. Let me just point out why that implies the desired implication. So suppose this inequality holds. Every flow has value at most every cut. And imagine you just sort of plot it on the real line. So 0 on the left, plus infinity on the right. Imagine you just sort of conceptually plotted the value of every possible flow of the graph and every possible cut of the graph. So you're going to get a bunch of blue X's for the values of flows, and you're going to get a bunch of red O's for cuts. Okay. What does this say? This says there's never an X to the right of an O. Right? That's what this says. So you have all the X's, then you have all the O's. So imagine, right, good. So why is it that if 2 holds, then 1 holds? So suppose you could actually find a cut AB and a flow F so that the flow's value equals the cut's capacity. In this picture, that would correspond to an X and an O exactly superimposed. Okay? There'd be an X and O on top of each other. That's what condition 2 would give us. If that's true, well, because no X can ever be to the right of an O, no other flow could possibly be bigger. Okay? So put differently, if every cut is an upper bound on every flow, if you ever get in the happy case where there's actually a flow which is as large as the minimum cut, you can't possibly do better. That's the best case scenario, okay? If this is true. Okay? All right, so that's why if this is true, then we're done with this implication. So why is this true? Why is it true that the value of any flow is at most the capacity of any cut? Well, if this seems sort of like obvious to you, that's great. I mean, your intuition is fine and it's accurate. For completeness, I'm going to give a short algebraic proof. Okay? But if it seems like it's clear enough, that's fine as well. All right, so I'm going to prove this now. Okay? So fix a flow F and fix a cut AB. So I need to start with the value of F, and then I need to have a sequence of equations and inequalities culminating with the capacity of this cut AB. Okay? So we start with value of f. All right, so let's remember what the value of a flow is. That's just the amount of stuff going out of the source. Okay? So by definition, this is the value of f. Okay? Now, just for kicks, sort of convenient for me, I'm going to add a second term which refers to the edges coming into S. Recall from Tuesday, we're assuming that there are no edges coming into S without loss of generality. So that's vacuous. That's just, I just added 0, okay, just for fun. Okay. All right. So now what I'm going to do is I'm going to add this same expression. So notice, so first of all, I should say, notice what this is. This is the net flow out of S. Okay, flow out minus the flow in. Okay, so that's what this difference means. Net flow out from a vertex. So I'm going to add to this the net flow out of every other vertex of capital A, of the source side of the cut. Okay. So the claim is that this is exactly the same thing as if I sum over all of the vertices on the source side of the cut of the net flows. Do you see why that's true? Why I can just harmlessly add all these net flows for all these other vertices V in A? What is it about flows that lets me do this? Yeah? Right. Conservation constraints. Okay? So for any vertex other than the source or the sink, and notice, you know, S was already there, and T is not part of A, so we're only adding vertices that are not the source or the sink. They all have flow in equals flow out, i.e. this difference is just 0, okay? So I added a 0 here, I just added a whole bunch more zeros. You probably wonder why am I doing all this, but give me a second, okay? All right, so now we have to somehow relate this to the capacity of this cut AB, and the way to do that is to just think about this double summation in a different way. Okay? So this is very kind of vertex-centric, the way we've written it right now. But imagine we adopt the perspective of an edge instead. Okay? So fix an edge E, and let's ask the question, how many times does f sub E appear in this expression for a given edge E? So the answer depends, and it depends on which of the buckets of types of edges you're in. Okay? So if it's an edge where both endpoints are in capital B, then you have nothing to do with this expression at all. You never show up at all. Okay? Here's a little more interesting. Consider an edge where both endpoints are in A. Say the edge goes from V to W. How many times does FE show up in the sum? Well, it shows up once with a coefficient of +1, corresponding to the vertex V, the tail of the edge. And it shows up again with a coefficient of -1, for the vertex W, the head of the edge. So those are going to cancel. So for any edge inside A, it basically contributes 0 to this overall sum. Okay. Now, if you have an edge which is sticking out of A, going from left to right, say V is in A and it goes to W in B, so now W is missing from the sum. So that's not going to contribute anything. But for vertex V, this edge sticking out is going to contribute once times f sub E. Symmetrically, for any edge going from B back to A, it's going to show up once with a coefficient of -1. Okay? So the upshot being is, another way to write this sum is to instead sum over all the edges and ask how much does it contribute. Everything contributes 0 to this sum, except edges sticking out of A each contribute f sub E, and edges sticking into A each contribute a minus f sub E. Okay? So again, that's just writing the exact same number in a different way, in an edge-centric way rather than a vertex-centric way. Okay? All right, so just one more line and then we're done. So notice, what are we trying to prove? We're trying to prove that the value of f is bounded above by the capacity of the cut. Okay, so if there's an inequality, it's going to go in the bigger than direction. Okay? So, what's an upper bound on how big f sub E could be? The capacity, right? U sub E. Right? So we use the conservation constraints, we better use the capacity constraints. Here's where we do it. Okay, so the flow can't be more than the capacity. So if we replace FE with UE, we only get a bigger number. This stuff we're subtracting, but we know it's not negative. Okay, so if we no longer subtract something which is non-negative, we again get a number which is only bigger. So we conclude that this is bounded above by the sum of the capacities of the edges sticking out, also known as the capacity of A, B. Okay? And that's what we set out to prove. Okay. So that concludes the first and arguably the most annoying implication of the three that we're going to do. Okay? So if, in fact, you can exhibit a cut and you can exhibit a flow so that they have the same value, then the flow has to be a maximum flow. If you think about it, also that cut has to be a minimum cut for the same reason. Okay? All right. So that's a sufficient condition for a flow to be maximum. You can find a cut with exactly the same value. Questions? All right. So the second implication is almost immediate. So the next implication is going to be that 1 implies 3, excuse me. And I want you to think about the contrapositive. Okay, so actually think about why not 3 implies not 1. Well, suppose not 3. Okay, so suppose the residual graph does have an ST path. We need to show that it's not a maximum flow. Why? Well, if there's an ST path in the residual graph, we can just go ahead and run Ford-Fulkerson, tongue twister, for one more iteration. Right? So what does Ford-Fulkerson do? It searches for an ST path in the residual graph. If it finds one, then it augments flow along it, giving you a flow with strictly larger value. So as long as there is a path in the residual graph, you're not maximum. You can make more progress and exhibit a higher flow. Okay? So contrapositive is basically immediate, just by running an iteration of Ford-Fulkerson. Okay? So the last thing I owe you, why does 3 imply 2? Okay? So why is it that if you don't have a ST path in the residual graph, you actually can exhibit a cut whose capacity is equal to the value of the flow that you've got? Okay? And this is sort of a short and sweet proof. So the trick is the following. So assume 3. Okay? Assume this is true. Now, in our minds, we're going to run, say, breadth first search. Okay? Again, it's not really an algorithm. It's in the proof. So it's sort of a thought experiment. We imagine doing breadth first search from S in the residual graph. Okay? So, or depth first search, whatever. So it's going to find everything that's findable. Okay? That's how these graph search algorithms work. By assumption, it's not going to get to T, because there's no path from S to T. Okay? So breadth first or depth first search will make some progress. It'll get to some vertices. Call those vertices capital A. Okay? So let A equal to V and V, such that there exists a path from S to V in GF. Okay? So again, just run your graph search from S, see where you get stuck. You get stuck at A. Okay? So I want you to notice that because of assumption 3, property 3, A V minus A is an ST cut. Okay? Certainly S is an A. S can get to itself. Certainly T is not an A. Okay, that's by assumption. Can't reach T from S and GF. And that's it. And it's a partition. So it's an ST cut. Okay? And so the claim is that this cut will actually meet our desired property 2. So let's see why that is. I erased the Here's this picture. Okay? So, it's an SD cut and it doesn't look like this. Okay? Why? We ran graph search out of S and we got stuck at A. If you got stuck at A, you're not going to see arcs like this leaving A, right? If there were arcs that went from A to outside of A, the graph search would have gone farther and A would be bigger. Okay? So this is a special cut where there cannot be any arcs sticking out of A. Okay? There can be arcs going backward, that's fine. So this is in GF here, the residual graph, right? Because if there's anything going the other direction, A would have been bigger. So what does that mean? So that means that, thinking about edges back in the original graph G, we have every edge whose tail is in A and head is in B, that goes from A to B. Every edge of the original graph that goes from A to B has to be saturated. The current flow has to use its full capacity. Why? Well, consider an edge which is not totally saturated. Then in the residual graph, there's still a forward version of that edge. Okay? But if this edge is sticking out of A from A to B, and then in the residual graph, there are no edges going from A to B, it has to be that this edge is saturated. It has residual capacity 0. Okay? So again, if this was not true, this edge would be in the residual graph, A would have been bigger. You wouldn't have gotten stuck at A. Same reasoning. There is no flow on any edge of the original graph G which sticks into A. Okay? Why? Well, if in the original graph you have some flow on an edge sticking into A, in the residual graph, you then get a non-trivial reverse version of the edge for the undo operation. So sending flow backward into A gives you an edge sticking out in the residual graph. And again, if there was an edge sticking out in the residual graph, A would be bigger. We wouldn't have gotten stuck at A. Okay? So, when we do this breadth first search out of S, we get stuck, and we get stuck at a very special set. We get stuck at a set where all of the edges of the original graph going out are saturated, all of the edges coming in the original graph are zeroed out. What does that mean? That means, so if we call this inequality here star, so remember, in this derivation here, what was the bounds, what were the estimates that we used in the inequality? We said, oh, well, for all the edges sticking out of A, at worst, it's the capacity. All the edges sticking in, well, at worst, they're 0. They're at least 0. And for this particular cut here, all of these inequalities hold with equality. Okay? For everything sticking out, we actually have Fe equals UE. The flow equals the capacity. For everything sticking in, we actually have that the flow is 0. So for a general flow and a general cut, you just have an inequality like that. For this particular flow F and this particular choice of a cut, everything here is an equality. Okay? There's no inequality. It's all equations. So that means that the value of the flow that we started with equals the capacity of this cut A, V minus A, which is what we were trying to prove. Okay? All right. So star holds with equality. Okay? So that finishes the proof of this theorem. All right. So if there's no ST path residual graph, that's how you exhibit a cut with capacity equal to the flow value. Questions? Certainly you can examine this theorem in action in this particular example. So in particular, this cut A comma B is exactly the same as the value of this red flow 3. And you will notice that if you look at this cut, it is in fact the case that for all outgoing edges they're saturated. Okay, that's saturated, that's saturated, that's saturated. And for this incoming edge it is indeed 0. okay, as has to be true for a MaxFlow MinCut pair.
Quick question.
Yep.
For part 2, when we define the parts A and B,
Yep.
are they for GF or G?
Well, so GF and G have the same vertex set.
No, because like the vertexes that you can reach in GF might be different from the set of
Yes.
vertices you can reach in G.
Excellent point. So I just erased it. No, it's here. So GF. So when you define A in the proof, you define it in the residual graph. Yep. That's important. I mean, this is the one part where it's easy to get confused between the original graph and the residual graph. So the claim is that in the original graph, like in this one, outgoing edges are saturated and incoming arcs are zeroed out. Why? Because if any of that was not true, in the residual graph, you'd have edges sticking out. Okay? But there aren't because you got stuck at A. Okay? So it's sort of like the assumption is in the residual graph, there's no ST path that you get stuck, and then the conclusion is back in the original graph about edges out being saturated and edges in being zero. Yeah. It's a good clarifying question. It's definitely one of the things you just sort of get used to with practice, and that's one of the benefits of having a few lectures in a row in MaxFlow. You know, keeping track, the residual graph, the original graph, it's confusing. Everyone finds it confusing when they first learn it. Okay, so but we have a couple lectures to get used to it. I think by the end of them, you'll get used to it as well. Okay, so this theorem's true. So what? Well, as we pointed out, this certainly implies that the Fulks-Forkerson algorithm is correct. Okay, even just a special case of this, that 3 implies 1. So we have indeed a correct MaxFlow algorithm at this point. We'll talk about running time in a second. Let me deduce a few other things from this theorem. Like the MaxFlow MinCut theorem, which states that for every flow network, the max flow value equals the MinCut value. Okay? That's the MaxFlow MinCut theorem. You have a graph, two seemingly totally different kinds of objects. Okay? Flows from S to T, conservation, capacity constraints, yada, yada, yada. ST cuts. Okay? The exponential number of ST cuts. And of them all, you find the minimum one. Yet somehow these two objects are just getting at the exact same thing. One from the left and one from the right. Okay? So not only are the x's always to the left of the o's, but there's always an x and an o that are superimposed. Okay? So why does this follow? Well, we know that the max flow value can't be strictly bigger than the MinCut, because we proved, part of our proof showed that all flow values are to the left of all cut values. So there's no way that's strictly bigger. So why can't this be strictly smaller? Well, that's just because you take a graph, take a max flow, and then invoke this theorem. If you have what does this say? This says if you have a max flow, then I can find you a cut. This is part 2. I can find you a cut with the same value. Okay? So it's never going to be the case that the max flow is strictly less than the minimum cut. This theorem implies you can always get them to be exactly the same. So that's the MaxFlow MinCut theorem. Okay? And it's always sort of a real pleasure for me to teach it, because really a long time ago, this is the theorem that seduced me into a career in algorithms when I was a student. I just sort of couldn't believe that something which seemed like such a mess just came together and you had this primal dual min-max theorem. It was just like, dude, there's some beauty in the universe. That's what I thought when I saw this theorem. So, your mileage may vary. So, okay, so that's just kind of a structural implication. Let me just mention a quick algorithmic implication of the proof, which is cool. So suppose I gave you a maximum flow in a network for free. Then, in linear time, you can recover a minimum cut. Okay? So in this sense, minimum cut reduces in linear time to maximum flow. Do you see where that's true? You see where the proof implies that? It's the very last step of the proof. So how do we prove that third implication? Well, we took, as an assumption, a MaxFlow F, and then we did a search from S in the residual graph to see how far we got. And then at the end of the day, it turned out that was a MinCut. At the time, we were just doing that in our minds in the proof. But that's a perfectly good algorithm. So if I give you a MaxFlow, in the residual graph, do BFS or DFS from S, look at how far you get, that's the source side of a MinCut. Okay, and this proof shows that. All right? So MinCut reduces in linear time to MaxFlow, and actually in practice, this is typically the method of choice. So if you need to solve MinCuts in practice, and we'll see examples later where you want to do that, often the fastest way to do it is just take an off-the-shelf super fast MaxFlow algorithm and do BFS to recover the MinCut. Okay. So any questions about that? So let me pass this around. So a little bit, before we move on to algorithms, which is the next thing, a little bit about the backstory. So how many of you have heard of the RAND Corporation, R-A-N-D? Just curious. Okay. So RAND is sort of a famous military think tank that was started after World War II. Many famous mathematicians, economists, etc., have passed through RAND, and that's where Ford and Fulkerson were in the mid-50s when they were doing this work. And so what happened is these two people, they've got their names here. So Harris, there's an Air Force researcher, Theodore Harris, and a retired Army general, Frank Ross. And so they came to Ford and Fulkerson for help. So Harris and Ross, the CIA, so keep in mind this is the middle of the Cold War, okay, mid-50s, which happily, none of you had to experience. So back then, there was the Soviet Union, and then there was the West, and there was this Cold War. And so the CIA had given Harris and Ross the rail system connecting the then Soviet Union to a bunch of Eastern European countries. So Poland, Czechoslovakia, Austria, Eastern Germany, this kind of thing. And so, they gave them really a network, okay, with vertices. The vertices represented kind of administrative districts, and the capacity, there were edges if there were train tracks, and the capacity was how much stuff, basically how much those train tracks could carry. And so Harris and Ross, through trial and error, basically through using heuristics, they had actually computed a flow in the network. And by the way, the handout shows you a picture of exactly what they did. So they'd computed a flow of 163,000 units through this network, and they'd found a corresponding minimum cut. The minimum cut is labeled the bottleneck in that diagram. So they knew that MaxFlow equaled MinCut in this particular network. Okay, and then they brought it to Ford and Fulkerson, who proved that MaxFlow equals MinCut always. And also they gave some provably correct algorithms for it. So Harris and Ross, it turns out they're actually more interested in MinCut than MaxFlow. They didn't really want to ship stuff through the Soviet Union's rail network. They wanted to blow it up as cheaply as possible and sever the connection between Eastern Europe and Soviet Union. So that's where this all comes from. All right. So, how about running time? How about computational efficiency? Okay. How long does it take, say, the Ford-Fulkerson algorithm to compute a MaxFlow? Well, it turns out it can take a long time, actually. And so this is something I'll ask you to think about on exercise set number 1. It can take a long time in the sense that if the capacities are very large, really big numbers, then it can take an enormous number of iterations to terminate. So it's what's called a pseudo-polynomial time algorithm, something you might have seen when you studied, say, knapsack in CS161 and a dynamic programming algorithm for it. Okay, so that's the bad news. When the capacities are big, this algorithm can really take forever. As you'll see when you come up with this example, the reason Ford-Fulkerson can take forever is because it can basically keep choosing a really sort of silly path over and over and over again and make very little progress when some other path would have let it make a lot of progress. So this motivates specializations of Ford-Fulkerson. Remember, in the basic FF algorithm, if there's many ST paths in the residual graph, so far we're just choosing arbitrarily. But maybe if there's many ST paths in the residual graph, one makes more sense than another. So that brings us to the Edmonds-Karp algorithm. From the early 70s. And this is the very natural specialization of Ford-Fulkerson, where amongst all of the ST paths in the residual graph, you augment along a shortest path. Shortest in the sense of it has the fewest number of edges, fewest number of hops. Okay? So that's the Edmonds-Karp maximum flow algorithm. Okay? Certainly it's correct, just because it's a sort of special case of Ford-Fulkerson, which is correct. But the running time, while not exactly blazingly fast, is still bounded by a polynomial in the input size. So what I'm going to argue next is that this algorithm, always augment along the shortest path in the residual graph, gives you a running time of m squared n, big O of m squared n. Always in this class, m will denote the number of edges, and n will denote the number of vertices. And then the applications that we care about, typically the number of edges is going to be somewhere between like n, that's for sparse graphs, and like n squared, that's for a dense graph. Okay, so that's sort of where m is with respect to n, which means in terms of n, this is going to be somewhere between n cubed in the sparse case and n to the 5th in the dense case. Okay? So that's kind of not very good, frankly. But notice that this bound holds no matter how big the capacities are. Okay? So this is a really good starting point. And then we'll move on to see some optimizations. Okay, faster algorithms. You may wonder, why do we study the slow algorithm if we're going to study fast ones later? Well, a lot of the important ideas are most gently introduced in the original Edmonds-Karp algorithm. Okay. All right. So how do you get this running time bound? Well, this follows from a Keylemma. Can I fit it in that space? Yeah. So let me tell you about the intuition behind this Keylemma. Okay? So to argue that it runs fast, we need to argue that the algorithm makes, in some sense, rapid progress. So what would be a notion of progress in the maximum flow problem? Actually, there's a lot of answers to that question. You'll see some other answers on the homework. But for the next couple algorithms, we want to think of it as follows. What are we striving for? We're striving to get to a point where in the residual graph, there is no path from S to T. That's our sufficient condition for optimality. Okay? So we want to disconnect S and T in the residual graph. So one notion of progress is if S and T keep getting farther and farther apart from each other in the residual graph. Okay? And again, distance here is number of hops on a shortest path, a minimum hop path. Okay? Now notice, right, the largest possible finite shortest path distance between two vertices would be n minus 1, if n's the number of vertices. Right? Because if you had a path with n edges, it would loop, and then if you threw out the cycle, you'd get a shorter path. Okay, so the biggest finite shortest path distance is n minus 1. If it ever gets bigger than that, it has to mean it's infinite. It has to mean you're disconnected. Okay? So that's the intuition here. Our progress measure will be how far S and T are apart from each other in the residual graph. If we can argue that that goes up reasonably rapidly, then we should be good. Okay, so fix a network G. Think of that as fixed. And we're going to be computing a sequence of flows as usual. And given a flow F, d of F is just going to be the distance between S and T in the current residual graph. Okay? Fewest number of hops. So ST distance in GF. Okay? Now again, don't forget, so G is fixed. The original network G is fixed. F keeps changing. Every time F changes, the residual network changes. And so when the residual network changes, this number D of F might change. Okay, so we want to track this number as Edmonds-Karp proceeds. All right, so what's the assertion? So first of all, D of F never goes down in the Edmonds-Karp algorithm. So it might stay the same, but it doesn't go down. Now, if it stayed the same forever, that would bode ill for us. So we have to say that it goes up at least sometimes. And indeed, we'll prove that it increases at least once per m iterations. Okay? So maybe at the beginning of the algorithm, the distance between S and T is 2 hops. We augment along a path, it's still 2 hops. We augment along another path, it's still 2 hops. But then at some point, we augment along a path, and it becomes, say, 3 hops. Okay? Do you see why this lemma implies our theorem? So first, instead of running time, let's just think about the number of iterations. So how many times, so again, assuming that this lemma is true, how many iterations could the Edmonds-Karp algorithm possibly execute before terminating? So how far apart can S and T be before they're disconnected? Right. So as soon as they're, if you know their distance at least n hops apart from each other, you know they're actually disconnected. Okay? So that says, and maybe I should say that, you know, this value D of F, that's an integer, obviously. It's a number of hops. So this can only get triggered n times. Yeah? Because after that, you're disconnected, and we know we stop. And this says that it goes up at least every m iterations. So Edmonds-Karp will only ever run n times m iterations in total before finishing. Okay? So that's the iteration bound. Where's the running time bound come from? Well, you have to actually, you know, find the shortest path. Now, maybe when I say shortest path, the first thing you think of is Dijkstra. But notice that's overkill here, right? Because we're just looking at hop count. Shortest paths with respect to hop count is already solved by breadth first search. Okay? So every iteration of Edmonds-Karp will be breadth first search, linear time, O of m time, O of m times n iterations. That's where the m squared n running time bound comes from. Okay? All right, so let's prove the lemma then. All right, so proof of Keylemma. It's short, but it's also a little tricky. Okay? So there's 2 parts, right? We fixed our network, we fixed our graph G, we're running Edmonds-Karp, F keeps changing, we're tracking the ST distance in the residual graph. Part 1 says it never goes up. Sorry, it never goes down. Okay? It can only go up. All right, so here's the right way to think about Edmonds-Karp. Okay? So in terms of what's called a layered graph. So obtain L sub F from G of F. Okay, so this is the residual graph as usual. This is going to be a subgraph. So basically, we're going to take the residual graph, we're going to throw out some of the edges, we'll be left with L sub F. L here stands for layered. So which edges do you keep? Here's what you do. Okay? You start from S, so you've got the residual graph, G sub F. You start at the source S, you run BFS, breadth first search. Okay? And then you just stop when you get to the sink, T. Okay? And you retain all of the forward edges in breadth first search, meaning edges that go from some layer I to some subsequent layer I plus 1. Any edge in breadth first search which went sideways within a layer, you throw it out. Any edge which went backward on your layers, you throw it out. Okay? So you keep in L sub f only the forward breadth first search edges when you run BFS from the source in the residual graph. So here's the picture. So in the residual graph, you've got some vertices that are one hop from S, meaning there's literally an edge from S to these vertices in the residual graph. So that's layer 1. Then you've got your vertices which in the residual graph take 2 hops to get to from S, but that you can indeed get to in 2 hops. So that's your second layer, and so on. And then finally you have T. Maybe there's some other stuff here, but we don't care. And then by definition, this is D of F hops from S. Remember, DFF is defined as the distance between S and T in terms of number of hops in the residual graph. Okay? So layer 1, so you can think of the source as layer 0, this is layer 1, layer 2, layer 3, blah, 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 all the way up to layer D of F. Okay? So remember, just like a basic property of breadth first search, which you learned in 161, is when you draw this layered graph, there's no shortcuts. Okay? There's no way you can get from like layer 3 and traverse a single edge and get to layer 7. Okay? That would violate what breadth first search does. Right? Otherwise, that thing in layer 7 would actually be in layer 4. All right? So edges can only either go forward, and if they go forward one layer at a time, or they can go sideways, but then we throw them out, we don't keep them, or they can go backward, any number of layers, we throw those out too. Okay? All right, so is the definition of this subgraph clear? It's an important concept. Okay, so why did I do this? Why should we muck around with this layered graph? Basically, it's a really good way to think about the shortest paths in the residual graph. And remember, Edmonds-Karp augments on shortest paths. So in other words, this is a good way to think about the types of augmentations that Edmonds-Karp restricts itself to. So in particular, and again, this is really just properties of breadth first search. If I think about the paths from S to T in the layered graph, those are exactly the same as the shortest ST paths of the residual graph G sub F. So the ST paths in the layered graph are exactly the same as the shortest ST paths of GF. Okay? One direction should definitely be clear. So suppose you actually had a path in the layered graph. What does that path have to look like? Well, it just marches one layer at a time. Okay, one hop to get here, second hop to get here, third hop to get here, and so on. It gets to T in exactly D of F hops, and D of F by definition is the shortest path length. So it's clear that any path from S to T in the layered graph has to net a shortest path in the original graph. Conversely, think about any path from S to T in the residual graph G sub F, which is not a path in the layered graph. So how would you not be a path in the layered graph? Well, you either have to go sideways or you'd have to go backward, right? Because all the forward edges are in the layered graph. So say you go sideways, say you look at a path in the residual graph that goes layer 0, layer 1, layer 2, stays in layer 2 again, then goes 3, 4, 5. Well, it wasted a hop. It's going to take D of F plus 1 hops to get to T. Okay? Similarly, if you ever take a backward edge, you're going to be stuck with at least D of F plus 2 hops to get to T. So those are not shortest paths. Okay? So the upshot is that the layered graph just succinctly encodes all of the shortest paths in the residual graph. And those are the paths on which Edmonds-Karp routes flow. Okay? All right, so I think we should do an example. Make this a little more concrete. So let's return to sort of our favorite running example. All right, so the way I'm going to do this, so I'm going to draw these networks. The solid edges, those will be the edges that are in, so I'm always going to draw the residual graph, but some of the edges will be solid, some will be dashed. The solid edges will be in the layered graph, the dashed edges will not be in the layered graph. They'll be omitted from it, okay? So, here's our usual kind of running example. So here the layered graph omits the edge 5. Why does it do that? Well, the S, so the source is basically layer 0. These two vertices are layer 1, right? Because you can get to each of these in one hop from S. So initially there's no flow, right? So the residual graph is just the original graph. So the first layer are these two. That means the 5 edge is a sideways edge, so it gets omitted from the layered graph. And then this is layer 2 here. Okay? So is that everything clear so far? What the layers are and like what's in and what's not in the layered graph? Okay. So what does Edmonds-Karp do? Edmonds-Karp augments along some shortest path in the residual graph, i.e. some path of L sub f. So some path that's all solid edges. So it has a choice here. It can either use the top one or the bottom one. Those are both shortest augmenting paths. It doesn't really matter, so let's just choose arbitrarily that it picks the top one. How do things then change? Well, so let's see. So these two arcs are untouched. So we still have this 2. We still have this 3. This arc got saturated, so we just pick up the reverse version. And then this has both a forward and a reverse version. Oops, and the 5 is still here too. So what is layer 1 now? Has it changed? Layer 1 is the same as before. It's true the capacity here is less, but that edge is still there. It still has residual capacity 1. So you can still get to each of these vertices in one hop. So this edge is still a sideways edge. It's still going to be out of the layered graph. And now this is layer 2. Okay. So here DFF was 2, and here DFF is still 2. So this shows that indeed, when you do an augmentation in Edmonds-Karp, there's no guarantee that the source sink distance will strictly increase. That may not happen. Okay? Didn't go down at least, so that's good. Okay? So just to remind you what we're trying to prove that it never goes down and it goes up at least once every m iterations. Okay, so then the last one. Okay, so what does Edmonds-Karp do here? It routes on a shortest path, i.e. on some path of solid edges. There's only one such path now. Right? So Edmonds-Karp will definitely route 2 units on that bottom 2-hop path. That's the only thing it can do. Okay? And once it does that, here's what the new residual graph looks like. All right, so we still have this 1 and this backward 2. The bottom left one we've now saturated. So this is now backward 2. This backward 2 is still there. Here we now still have 1 unit going forward and we have 2 units going backward. And so this edge, which had always been dotted, the cross edge, it's no longer dotted. Okay, it's now a solid edge. So that's 5. Okay. What are the layers? Well, so what vertices can you get to from S in one hop? Only the top one, right? Only the top vertex can be reached in one hop from S. So this is layer 1. What's layer 2? So which vertices can you get to in 2 hops from S? Well, only that one, right? Because again, this arc is saturated, so it's dropped out of the residual graph. So this is layer 2, and this is layer 3. And we see that in this case, in fact, the ST distance in the residual graph has gone up strictly from 2 till 3. Okay? From here, we do one more augmentation, and we get the MaxFlow, and we're done. All right? So what this whole lemma is about, that we're taking this detour from, it's showing that what we're seeing in this specific example is true in general. Okay? The source sink distance might stay the same for a while, but it's got to go up periodically, and it never goes down. Right? So do you have some feel for that now? Any questions about the example? Yeah.
So it seems that we're doing the breadth first search, we're treating it like an unweighted graph. However, we're implicitly weighting it because we're removing the edges that have 0 weight.
You're right. You're right. So really, so I've been a little imprecise about what the residual graph is. The way I defined it, I said include 2 edges from every edge of the original graph. And now in general, and in all the pictures, I've been noting that some of those are 0. Either they're saturated, so you don't have the forward arc anymore, or you haven't routed anything on it, so you don't have the reverse arc. So I've been omitting those in the picture. And you're absolutely right, that when I say do breadth first search, I mean do breadth first search only on edges that have positive residual capacity. Because remember, at the end of the day, when you find a path, you need to augment. So you better find a path where every single edge has positive residual capacity. So that's what you do the search in. It's a good question. Other questions? All right. So now that we have a little bit of confidence from our examples, let's actually prove it. Prove the Keylemma. So part 1 just says that when you augment on a shortest path in the residual graph, the ST distance can't go down. Okay, so why is that true? Well, so Edmonds-Karp augments on a path of LH, of the layered graph, LF. Okay? So this is using this note up here. Right, so Edmonds-Karp by definition uses some shortest path in the residual graph. We observed that that's a 1-to-1 correspondence with the paths in L sub f. That's the whole point of defining L sub f. Okay? So these are the paths that Edmonds-Karp uses. Now, what are we worried about? We're worried that somehow some newly shorter path appears after we do this augmentation. Okay? So currently, we have a residual graph where maybe it takes 5 hops to get from S to T. Okay, so there's 5 layers. We're worried that we do an augmentation, suddenly we could get there in only 4 hops. Okay? So how could that possibly happen? Well, the only way it could happen is if the augmentation introduced some shortcut edge which catapulted over at least one of these layers. Right? So if suddenly there was an edge which went from layer 2 to layer 4 in this network, then conceivably there'd be a shorter path to T than there was before. But there's no way this can happen. This augmentation cannot create such shortcut edges. Why? Well, what are the edges which newly appear after an augmentation? It's the reverse edges of the augmentation you just did. Okay? Those are the only new edges you might have in your graph. Okay? You augment forward, you get a reverse arc with non-zero residual capacity. But every edge that we augmented on went forward. It went from a layer I to a layer I plus 1. So the new reverse arc goes from layer I plus 1 to layer I. It goes backward. Okay? So we certainly don't introduce any new shortcuts by doing an augmentation on a shortest path. Okay? So that's why, that's basically the proof. So newly created edges go backward. Backward in the sense of that picture of those layers up there. And so that means no new shorter paths are created. Okay? So that's part 1 of the lemma. Any questions about that? All right. So that's good. It can't shrink. Why does it have to eventually go up? So part 2 said that at least once every m iterations, it's going to strictly go up by at least 1. Okay? And that's all we have left to prove. Well, So as long as d of f stays constant, okay, so maybe the distance between s and t is like 5. We do an iteration, it's still 5. We do an iteration, it's still 5. And we just watch what happens. Okay, we say, how long can this go on? Okay. Well, as long as the st distance stays constant, say it's always equal to 5. The first claim is that every iteration zeroes out at least one edge of L sub f. Okay? And this is just, by the way, we choose the parameter delta. This is just because we're greedy. Right? We find a path on which we can augment, and we augment as much as we can, subject to the residual capacity constraints. Okay? And so then, what does that mean? That means whatever edge on this path has the minimum residual capacity, it's going to get knocked out of the residual graph. Okay? Because we'll just totally saturate it, or if it's a reverse arc, we'll totally zero it out, and it'll disappear. Okay? So at least one edge, the bottleneck edge of a path, disappears every time we do an augmentation. Okay? So that's the first point. We'd like to say, oh, well, there was only m edges. If one of them goes away every time, then we have to, something else has to happen after m iterations. The one tricky point is we have to argue that it doesn't come back. Right? The worry is that sort of, we kill an edge over here, but then we do some other augmentation, and all of a sudden it reappears because we augmented along the reverse arc. Okay? So that's the one subtle point. But that can't happen. And the reason it can't happen is really just the same as the proof of part 1. Okay? So imagine you had an edge in the layered graph. Say it went from layer 3 to layer 4. Okay? And so say that was the bottleneck edge, so that's the one that got saturated in some augmentation, so this edge from 3 to 4 dropped out. Okay? The only way it could ever reappear is if we augmented flow in the other direction along that edge. Okay? But that would be augmenting from layer 4 to layer 3, which would be a backward path. Edmonds-Karp only ever sends flow on forward paths. It never routes flow backward, so it's never going to reintroduce a forward edge that we had previously zeroed out. Okay? So we drop an edge every time, and we have this monotonicity property that once it drops out, it can't reappear at least until the shortest path distance gets bigger. Okay? So that's it. That's the proof of the Keylemma. So one thing I want to point out is that, when the shortest path distance does change, so remember all of this was just saying consider a sequence of iterations where the st distance stays the same. When the st distance actually goes up, then things can change quite a bit, right? So that's like the difference between this network here and this network here, okay? And so for example, we had something like an edge which had previously not been in the layered graph, all of a sudden does become part of the layered graph. And that's because this edge didn't participate in any 2-hop paths, but it did participate in a 3-hop path, so it had to wait till all the 2-hop paths were sort of severed by augmentations, then all of a sudden it would be part of a shortest path again. Okay? But while the shortest path distance stays fixed, edges only go away and they don't come back. Yep?
So here, it looks like we implicitly assume that the layered graph does not change when we augment the shortest path in each iteration.
Yeah, so it's a good question. So it's changing, but if you like, just think about this partitioning of the vertices. Okay, so at the beginning of this sequence of iterations, you have vertices v1, vertices v2, vertices v3, and so on. And it's, by definition of BFS, the only way to get from S to T, using only, say, 5 hops, is to use a sequence of forward edges, and you need at least 5 hops to do it. And so with respect to that definition of these vertex groups, everything I said is correct. Right? So, if an edge goes from v2 to v3, you augment, you get a backward edge from v3 to v2. If you try to use an edge from v3 to v2 to get to t, it means you have to go backward 1. It's going to take you d of t plus 2 hops to get to t.
But a vertex can go from a layer which is 2 hops away.
So I understand, but just freeze this once and for all. Okay, so look at the first iteration where d of t equals 5. Look at this graph. And now just, in your head, freeze membership of vertices in these groups forevermore. The residual graph will keep changing, but we sort of saved a copy of what this graph looked like the first time d of f equaled 5. Okay? And so then it's still true. The only way you can get from S to T is you have to go layer by layer. And none of the augmentations, because you only go forward, all the new edges go backward. So at no point will you get a shorter path. It's also the reason why at no point will something reappear until D of F changes. But you're right, it's a subtle point. It's a good question. Other questions? Okay. So I want to wrap up by just giving you a very brief introduction to something quite related to Edmonds-Karp that you're going to explore mostly on the exercise set and the problem set. And it's known as using blocking flows to compute maximum flows. And the idea here is that we're going to augment not just along one path at a time, but on a batch of paths all at once. Okay? So this is known as Dinic's algorithm. So this is roughly the same time and independent of Edmonds-Karp. And it's pretty similar, actually, despite being developed independently. So you start with a zero flow. And as long as there's some ST path in the residual graph, so notice, right, this is a great stopping condition to have, because if this algorithm stops, it stops with no ST path in the residual graph, so it's going to be optimal, right? By our first result from today. So construct the layered graph LF from the residual graph GF via breadth first search. Now, I've sort of done a sleight of hand here, actually, because before when we were talking about the layered graph, it was all like inside the proof. It was just a thought experiment, right? Edmonds-Karp just found its shortest path. In Dinic's algorithm, we're actually going to explicitly in our algorithm compute this exact same layered graph previously shown in the analysis, okay? That's just a breadth first search computation, so that's linear time, no worries. Then we're going to compute what's known as a blocking flow, and I'll tell you what that is in a second. Compute a blocking flow in the residual graph, which in general is not one path, but a superposition of a bunch of paths. And then we augment F by this entire superposition of paths G. Okay? So that's the high-level structure of Dinic's algorithm. You just keep computing blocking flows in the current residual network. So what's a blocking flow? A blocking flow is just where our very first naive greedy algorithm is exactly where it gets stuck. Okay? So remember, our first greedy algorithm didn't even have a residual graph. It just tried to keep pushing flow upward on edges. If it ever got to the point where there was no path from S to T, where every edge was below the capacity, that's where that naive greedy algorithm halted. That's called the blocking flow. So if you can't find a path where everything is under capacity, that's a blocking flow. So blocking flow G is by definition so that there is no path such that there's room left on every path. So this is no, so I should say there does not exist a path in G, okay? So it's not talking about the residual network, it's talking about just some graph. And so the example you want to have in mind is the same place where our greedy algorithm got stuck. Which is this flow here. Yeah? So if you send 3 units on the zigzag path, then this edge is saturated, this edge is saturated, so there is no path from S to T, which uses only unsaturated edges in the forward direction. Okay? So this is a blocking flow. Okay. So on the first exercise set, I ask you to prove the following. The reason it's just an exercise is because the proof is almost exactly the same as the proof of the Keylemma we just went through. Okay, but I want you to think through the details of that. So the claim is that if G is a blocking flow in the residual network G of F, Then, when you augment the flow F using this blocking flow G, this ST distance is guaranteed to strictly go up. Okay? So for comparison, remember Edmonds-Karp. We were augmenting on just one path, and we couldn't say that the ST distance went up. We could say it went up once every m iterations. Now we're doing a batch processing. We're augmenting not by a path, but by an entire blocking flow. And the benefit is every blocking flow is guaranteed to increase the ST distance. That means we don't have to do more than n blocking flow computations before we're done. Because again, remember, once S and T are n hops apart, they're infinite apart, and we're done. We have a max flow. Okay? Oh, whoops. Then the distance between S and T in the residual graph after the augmentation is strictly bigger than what it was before the augmentation. Okay? So that's on exercise set number 1. As far as the implications for running time, so how fast does this algorithm run? Well, kind of obviously, it sort of depends on how fast it takes you to compute a blocking flow, right? Computing as short as path was not hard. That was linear time. Right? Now we're trying to compute a possibly more ambitious object, a blocking flow. It might take more than linear time. Okay? But parameterized by whatever your blocking flow subroutine takes, we can at least say that Dinic's runtime is O of n times the time needed for a blocking flow. Okay? So you just give me as a black box a subroutine that will compute a blocking flow in a graph. Dinic's algorithm just uses that subroutine as a black box. By the claim, it only needs to invoke the black box n times. So the running time is just n times that of the subroutine, n times a blocking flow. Okay? So how fast can you compute a blocking flow? Well, so on the first problem set, I'll ask you to think about how you can basically use depth first search to get a running time of m times n for a blocking flow. Okay? So if you plug that into Dinic's runtime, now you get mn squared. Okay? And that's an improvement over the Edmonds-Karp running time, right? So m squared n, definitely worse than n squared m. It's always good if you can replace an m by an n, which is only going to be smaller. Okay? So it's going to be n to the 4th at worst, this one. As far as the state of the art, it's even known how to get, using sort of fancy data structures, you can compute a blocking flow in close to linear time, meaning like an extra log factor, so sort of Dijkstra type running time. So that gives you MaxFlow algorithms with running time pretty close to m times n, which is now not so embarrassing anymore. You've seen some running times like that before in 161. So that concludes the story with augmenting paths and blocking flows. Next up is a different paradigm for MaxFlow called push relabel. It's a little less intuitive, which is why I do this first. But push relabel has the benefit of being really usually the choice in practice, really blazingly fast maximum flow algorithms from push relabel. We'll talk about that Tuesday.